AdvSim, generating safety-critical scenarios for self-driving vehicles. As self-driving systems become better, simulating scenarios where the autonomy stack is likely to fail becomes important. However, identifying these scenarios is challenging, as there are exponentially many of them. In this paper, we proposed AdvSim, a framework to automate the generation of worst-case scenarios for self-driving vehicles. Most previous works generate adversarial scenarios only for a handful of scene configurations, and are adversarial only with respect to a planning module that takes the ground truth actor states as input. We propose a scalable approach to modify existing traffic scenarios to cause full autonomy system failures. Our approach tests the full autonomy system and generates over 4,000 unique adversarial scenarios. We frame the generation of worst-case scenarios as a black box adversarial attack. AdvSim works as follows. Given an existing scenario and its original sensor data, we first perturb the actor's trajectories in a physically plausible manner. Next, we update the sensor data to take the actor perturbation into account. We then evaluate the autonomy system on the modified scenario, compute an adversarial objective, and update the proposed perturbation using a black box search algorithm. AdvSim works for any LiDAR-based autonomy stack. AdvSim's goal is to increase the risk of the autonomy system's plan, tau star. Our adversarial objective consists of an imitation loss representing the deviation from the expert trajectory, a safety loss to encourage collisions with other actors, and traffic rule and comfort costs that encourage the autonomy's plan to have lane violations and to be dangerous. To ensure realism of simulated behaviors, we parameterize the actor behavior with the bicycle model and set physical constraints such as staying on the road and not colliding with other actors. Given the perturbation on the actor's motions, we now conduct realistic LiDAR simulation to accurately reflect the updated scene. The modified LiDAR history is the new input to the autonomy system. The video shows that the generated scenes are realistic and matches the desired perturbation. We now show AdvSim generated scenarios for the P3 autonomy system. We focus on an open-loop scenario evaluation setting in which the evaluated autonomy systems take the past 1 second LiDAR data as input and outputs a 5-second trajectory plan. We then unroll the 5-second plan and the other actor's trajectories for 5 seconds, and evaluate the autonomy system's performance during that time horizon. The SDV is in blue and the perturbed actor is highlighted in red. This scenario has a stationary bus in front and a crossing pedestrian. In the 5-second trajectory output from the P3 system, the SDV only moves forward a little. AdvSim perturbs the initial states of the bus in red by moving it into the left lane. Now, the P3 autonomy system does not detect the pedestrian, and the SDV's 5-second plan collides with it. To understand why the SDV behaves as it does, we now show the forecasted occupancy visualizations of the P3 autonomy system. The occupancy for pedestrians is shown in light green. As we can see, the pedestrian is perceived as part of the bus's occupancy area, and hence the system misses the pedestrian detection. Here's another example. Originally, the blue SDV lane changes smoothly to avoid the stationary bus in front. AdvSim perturbs the bus to instead be reversing and blocking the road. Now, when the SDV attempts to lane change, it is rear-ended by a high-speed vehicle from behind. From the occupancy visualization, we can see the predicted bus occupancy blocks the whole lane. This causes the SDV to predict a dangerous large turn to avoid the bus, but does not properly account for traffic from behind. AdvSim generates challenging scenarios for a wide range of state-of-the-art autonomy systems. As we can see, these systems initially achieve a relatively low collision rate on the natural real-world scenarios. But with AdvSim, we increase the collision rate on average by over 200% compared to the original set. These challenging and physically plausible scenarios provide insight into how different autonomy systems compare and how they fail. AdvSim scenarios can also be used in autonomy system training to improve performance. We take 2 pre-trained state-of-the-art autonomy systems, PLT and P3, and fine-tune them on a dataset augmented with AdvSim scenarios. Robust training with AdvSim generated scenes helps improve the performance on both the original and adversarial scenarios, making the autonomy systems safer. In summary, we propose a scalable adversarial framework to simulate challenging scenarios for autonomy. These scenarios are valuable for both testing and training any autonomy system. Please see our paper and poster for more details. Thank you.